fridge, don't
Are you able to switch off your fridge?
really? Jesus. This is what I have to put up with every week. Every week.
Oh yeah, no, and I have to edit out the fridge.
So are we actually recording?
Yeah, we're recording. We're good to go.
The Interplanetary Podcast. The exploration of space for the benefit of all mankind. Your hosts here in London, Matthew Russell and Jamie Franklin.
Matt, it's podcast 26.
It is podcast 26.
What are your thoughts?
My thoughts are we have a special guest.
We do. We have the wonderful Harriet Brettle from the Planetary Society. I got it right this time. How are you, Harriet?
I'm very good.
Thanks for joining us again.
Thanks for having me again.
In the Kitchen of Dreams.
In the Kitchen of Dreams.
Is that what we called it last time?
Kitchen of Destiny, I believe.
Oh, Kitchen of Destiny.
So we're going to talk about a number of things, exoplanets, but the first thing we want to talk about is TRAPPIST-1.
Very exciting. Isn't
We should
it?
start there, shouldn't we?
Yes, let's. So, tell us all about TRAPPIST-1, Harriet, and with no mistakes,
Everything
like we do.
that I know.
Yeah.
So this was an announcement that NASA made a couple of weeks ago now, isn't it? So, old news, but very, very big news, which is really exciting. So, TRAPPIST-1 is a star system that is 40 light years from Earth. Mm-hmm. So, close, but not too close, so we can talk about going to visit sometime.
As we mentioned earlier, Centauri being 4 light years and this being 40, I got a bit upset when I realised we probably couldn't send a probe there that quickly.
Yeah, it's 10 times further.
Damn it.
And it was hard enough, wasn't it? It was like a lifetime of breakthrough starshot to get there.
Yeah.
So yeah, you're suddenly talking 10 lifetimes.
Oh.
It's pushing it for us, isn't it?
Yeah, it's a long way away.
Yeah.
But let's not go
on a positive.
On a positive
But
note,
very exciting.
We know that there's lots of planets, which is very exciting.
Yeah, that is super
right?
exciting.
So NASA announced that there are 7 known exoplanets going around this star, which is really cool. They are named TRAPPIST-B, TRAPPIST-C, TRAPPIST-D, E, F, G, and H. So they're very imaginative.
Yeah. They sat long. They thought long and hard about it.
No, I'm assuming TRAPPIST-A then is the star itself in kind of that talk.
Yeah, so there's a kind of standard naming for exoplanets, at least I've noticed. So the system tends to be known by the telescope that discovered it. So TRAPPIST actually stands for the Transiting Planets and Planetesimals Small Telescope.
Right,
affectionately known as TRAPPIST.
Rolls off the tongue.
Yeah, and then all of the planets are kind of B to whatever as they go out away from the star. So what can I tell you about these planets? They are in a solar system-like arrangement, which is very exciting. You must have seen the NASA images, right, that they've created of these. The travel posters are really cool, but also kind of a little bit of an explanation of what they look like and how they potentially could compare to our solar system. 3 of them are in their habitable zone, which means that theoretically that they are at the right temperature to support liquid water, which is one of the things that we look for when we're looking at potential life forming on other planets.
But could the other ones, if they've got a reasonable atmosphere, be also habitable? The ones further out, for example?
Yeah, absolutely. So if you have a dense atmosphere that can keep some of the heat in, that's definitely an option. If you think about our solar system, some of the areas of potential life are completely outside of our theoretical habitable zone, right? So if you read science fiction, you'll hear about Titan or Europa, right? It's potentials for life, and they're super far out. But because they've got Jupiter and Saturn and kind of this thermal heating effect that they get from orbiting around these giant planets, theoretically they could be at the right temperature to harbour life as well.
What I love about Titan is because it would be a sort of methane-based life, so it would have to survive in liquid methane rather than liquid water. I think that's a really exciting place to go and have a look, because you think, well, if life can start in liquid methane, I mean, imagine if you found life on Titan, it would more than open up than if you found life on Europa. Europa would be amazing.
I'll take life anywhere.
Absolutely.
That'd be good. But yeah, absolutely. I mean, there's so many different options, right? I mean, I was listening to, I can't remember which scientist it was who was saying this the other day, but if you think about the Earth, life on the Earth formed pretty quickly after the heavy bombardment stopped.
Well, they found a whole new bacteria, didn't they, quite recently, that's 300 million years older than the previous discovery. So it started even earlier than they thought.
That's even better
It's yet
news.
to be verified, but it looks very, very much like it is.
Yeah.
So So it's very, very soon after the Earth cooled down, and it's possible. Yeah.
Yeah. So if life appeared so quickly on our planet, then that makes it more likely that we might see it cropping up elsewhere.
Absolutely.
So
And so the 3 planets that are in the habitable zone, have they said which might be more susceptible for potential life, or is it just that they're saying at the moment we don't know enough?
So I think it's fair to say that we really don't know at this point.
Yeah.
I guess one of the things that we do know is the size of these planets and how far they are out from their.
So let's talk
from their
about
star.
size for a minute. So their star compared to our star, what are we talking about?
It is. Oh, I've got the data here. It's like you knew the questions to ask me. So this star, TRAPPIST-1, is an ultra cool dwarf.
Yeah, I'm laughing.
I mean,
You did mention it was my nickname at school. It wasn't really. I'm 5'8". It's not that bad.
but yeah, I mean, astronomers know all the cool things to name things, right?
This is it.
So this star is 8% the mass of our sun, around 11% radius of our sun. So it is significantly smaller than our star, probably more comparable to Jupiter than it is to our sun in terms of size. It's, like I say, it's ultra cool dwarf star, and that makes it really a great star for us to look at in terms of exoplanet detection. So the smaller the star, that kind of increases the probability that we'll be able to detect planets going around it.
I suppose it's a bit like trying to spot a fly flying in front of a low wattage light bulb rather than in front of a floodlight.
Yeah, so the method that was used to detect this planet system was called the transit method, and the way that works is essentially you have a telescope looking at the star, and as the planet, or planets in this case, pass in front of the star, the amount of light that you get when you're looking at it drops, because you have kind of a little blot blocking it out, right? You can detect the amount that the light dips, and from that you can figure out the size of the planet and how quickly it's orbiting around its star.
Right.
Yeah, exactly.
But how do you separate the timing? If there's multiple bodies, how do you separate the timing between the two? So say if one's, particularly if they've got sympathetic timing, how do you then extract that data? That's something I've always...
So what you have to do is a kind of time series analysis, so to speak. This is going to sound...
TRA?
TSA.
TSA.
Yeah.
What am I talking about? I've lost my acronising gene.
But what you can do is you can kind of overlap the periods. So you know that each of the planets, or you assume that each of the planets is orbiting around at a constant period. So like for the Earth, it's going around the Sun one time a year. So if you looked at the dip of light, so you were looking at the Earth-Sun system, you would see a little dip in the Sun's light once a year when the planet goes around, right? And the same is true in this TRAPPIST star system, right? So every X number of days you'd get a dip that corresponds to one of the planets, but every 3x days you would see a different shaped dip that would correspond to a different planet. So what you can do is, if you chop up the time that you're looking at the star into different time periods, and you overlay them with each other, you will see these dips that will happen always with the same frequency, with the same size of dip, and you can use that to correspond to the different planets.
So it is the size of dip, because one of the striking things about TRAPPIST-1 is that these 7 planets are unbelievably similar in size to the Earth, let alone themselves, but to themselves as well. So presumably the dip's similar for each one?
I don't know the answer to that question, I'm afraid. But in terms of the periodicity, you can figure it out. So let's say you've got one planet that's going around once a day, and you've got another planet that's going around twice a day, okay? So you're going to see this dip once a day, because that's going to be the first planet. But every second day, you're going to get a kind of double dip, because you're going to have not only the first planet blocking out the light, but you're also going to have the second planet.
Right.
And you can use that to basically take away one of the planets from the second dip, and then you've got the information of both of them.
But presumably there's quite a bit of maths going on to do 7 planets.
I think there's some pretty heavy maths going on there. Yeah.
It definitely is. So we've just talked about different types of star in relation to our sun. How do we know different types of stars?
So in terms of exoplanets, all of the exoplanets that have been discovered so far have been going around stars in our own galaxy. Because they're much closer than any others, right? So this is still kind of, the technology here is phenomenal. But we can actually see these things at all.
But it must be even like a small part of our galaxy. I mean, presumably we've not really looked much further than a tiny section of the spiral arm that we're seeing.
Oh yeah, so even now it's a tiny proportion of the number of stars in our own galaxy, right? We can talk about Kepler in a little bit, because that's one of the sources of a huge number of exoplanet discoveries. But that essentially is a space telescope that went up in, I think, 2009. And that just looked at a tiny segment of the sky. So it was looking at a kind of something along the lines of like a square inch of sky if you looked up in the evening. And that discovered over a few thousand exoplanets in that small section, right? So that's only looking at a very small fraction of the stars that we have. In our galaxy.
It just makes you think, doesn't it? Well, it's just a dip in the ocean, isn't it?
But what's really exciting about TRAPPIST is that it's finding a whole bunch of what must be rocky planets of a similar size to Earth, and you think, well, maybe this is maybe Earth-sized planets aren't that uncommon, because they haven't been easy to find so far, have they? I mean, most of the planets, due to the nature of the way that we detect them, are gas giants or super gas giants like Jupiter and Saturn and planets like that, the majority of the ones found so far.
Yeah, so one of the, I guess, surprising things that's come out of recent exoplanet discoveries is that a lot of the planets that we see are very different to ones we have in our own solar system.
Right.
Part of that is by nature of the detection method. So as we were talking about these dips going in front of the star, and that's how you pick up the planets, that favours small stars, because you have a smaller light to kind of see the dips, so the dips are enlarged. You also want planets that are very close to their star, because as with any scientific discovery, you need to replicate it, right? So you can't wait, well, you could, but you don't want to be waiting years and years to wait for that planet to come round again. You want to be looking at planets that are super close. So, I mean, for example, with TRAPPIST, these planets are going around on like every few days around their star, right? So you can see the dip going again and again and again. Even Mercury takes like 78 days to orbit our star. Yeah. So if you wanted to see something like Mercury, one, it's tiny, so you'd hardly see a dip at all. And two, it goes around so infrequently that you'd have to be looking at the sky for so long to pick it up.
For a long time to go.
There we go. Even harder to find, something like Pluto. That would just be a joke, wouldn't it? But I mean, what strikes me almost instantly is if you're using the transitory method rather than the way that stars wobble or whatever. TRAPPIST-1 seems to me that there's this insane coincidence that the plane of the orbit of the planets happens to be pointing at us. I mean, so how often can that? I mean, if you think about it, how often does that happen? Yeah, so I was actually in a class last week where we talked about this. If you think about it in terms of probability, it's not that unlikely that the star is going to be passing, at least in part, through your path of vision, right? So if you think about a disk, a loop, right, and that can be the orbit of the planet. Yeah. For you to not detect that planet, it has to be kind of orbiting face on to you, right? So it's going around this loop. It's not crossing across the path of the star at all. And there's only two options of how that can be structured, right? It can either be that disk can be one way, or it can be flipped, be the other way. Okay. If you think about a planet that is going around a star and it's covering the light when you see it, that disk. This is going to be really hard for radio, right? No one's going to be able to see my hands doing this like weird circling thing. Yeah. But if you think about the number of different combinations, that disk can be in any plane, really, in that kind of as you go around the circle. So it is quite. So it is still quite a significantly high probability.
Yeah. Okay. So there's much more There's many more situations where the planet will be crossing in front of your plane of vision,
Right.
compared to you wouldn't see it at
Oh,
all.
wow, that is really fascinating.
Yeah.
Because one thing I always used to think would be quite funny when Galileo picked up his telescope and looked at Saturn for the first time, how irritating it would have been had Saturn been in one of those orbits where its rings are absolutely face onto you, so you can barely see them.
Yeah.
And so you wouldn't have seen anything unusual.
Yeah.
Nothing to see here.
Yeah,
And then
move on.
Yeah, move on.
Yeah.
That
Well,
would
yeah,
be-
I mean, they're only like... how thick are
Well,
Saturn's
it's,
rings? And
a few
thin, it's like a
metres.
few
Yeah,
metres,
yeah, it's a
right?
few
You wouldn't be able to
metres,
see
yeah.
that at all. So.
No, they
Yeah.
do. It does disappear. Sometimes Saturn's really disappointing in a telescope when the rings just disappear.
Yeah.
Because it's they're full on, and then other times where it looks amazing. Mm-hmm. But I guess there must be star systems out there though then that we will never know if they've got planets going around them by using the transitory method. So, what are there a sort of host of other methods that we use to find planets?
Yes, there are. So I guess one example of a method that we can use to detect other kinds of exoplanets is radial velocity technique, or using the Doppler shift of a planet. So this was the way that Proxima b, that I think you talked about on the podcast
Yes.
already, was discovered actually by a team led by Queen Mary, University of London, so right on our doorstep here, which is very exciting.
Good work.
And that planet, Proxima b, does not transit across its star. So you cannot see the planet by using transit method. But what you can do is look at the... you can observe the star and observe the star's light. And as the planet-star system are kind of going or rotating around their joint centre of mass, the star appears to wobble because the planet has kind of sufficient mass that it's tugging the planet. Sorry, the planet has sufficient mass that it is tugging the star.
Yeah.
And so
both.
Or both. Yeah, exactly.
yeah.
It's a two-way street, right?
Two-way street, yeah.
So that kind of means that the star kind of wobbles a little bit on its orbit as the planet is going around it. And if you think about the light that is coming to you when you're looking at it through a telescope, half the time that star is moving towards you in its orbit, so the starlight is blue shifted towards you, and half the time it's moving away from you, so it's red shifted. And that difference in the spectra, so the difference in the amount that the light is shifted, means that you can figure out the mass of the planet that is orbiting it.
What's incredible is that when you see the spectrum of a star, obviously you know what the composition of that star is, but the fact that you can then shift it back and forth and have the accuracy must be just ridiculous. But I would have thought there must be a hell of a lot of noise in that data, so that you have to observe that quite a lot before you can get a statistical, whatever it is, sigma thing to actually get it, because that must be a very, very... Is that a harder technique to use than the transitory method?
So radial velocity came first. That was kind of the original exoplanet detection method. One of the things that's so extraordinary about radial velocity detections is the kind of speeds that you're looking at. So we talked about the difference in the star moving towards you and star moving away from you, and that shift. We're talking about meters per second speed differences here, and if you think about that in terms, that's kind of like walking pace. So you're looking at those kind of differences in speed and trying to figure out
incredible.
like it's absolutely extraordinary. And the technology has got so good that we can now measure differences in speed of less than a meter per second at stars that are light years away.
In other words, it could detect how I'm changed, like Usain Bolt changes colour as he runs towards the 100-metre line. Yeah. That's incredible, isn't it?
Yeah, it's remarkable.
Oh my god, it's actually blown my mind.
Yeah.
What?
Yeah. It's pretty extraordinary.
I mean, obviously you can hear it. I mean, what's incredible is that you can hear Doppler shift quite easily with sirens as they go past you at traffic lights, and it goes past you and you can hear it. But seeing it is something completely different, isn't it? I mean, that's extraordinary. Yeah,
and so the kind of this huge new wave of exoplanet discoveries has really been triggered by phenomenal advances in technology. So being able to get the precision down to that meter per second speed requirement that you need, and similarly for transit, if you're looking at a star that's light years away, to be able to measure a dip in the light intensity
It's incredible.
in a way that you need to detect those kind of planets.
Do you know what kind of percentage it dips? Is there a percentagey kind of thing?
Yes. So if you have Jupiter orbiting around the Sun at an Earth-like orbit, that would reduce the brightness of the star by 10%.
10%. That's quite.
Yes,
That's significant.
0.1. Yeah. If you were trying to detect an Earth in an Earth-like orbit around a Sun-like star, that would reduce the light by a 10,000th.
100%.
Yes. So that's like 0.01%.
Yeah. So
that's how much of a reduction in the light you get.
That's significantly small.
Yes.
Well, several
it's
magnitudes small.
much smaller.
Yeah. I mean, what's brilliant? Yeah, I mean, I do. What's a fantastic picture to look at with the with how much the star moves is how much our own sun moves in its orbit, and it doesn't even stay on a central point. It actually goes completely out of of a central point, and that's why some people would argue that the planet definition of Jupiter isn't quite right, because it doesn't orbit the sun. The sun and Jupiter actually orbit each other around a point outside of the sun's atmosphere.
That's interesting.
Yeah, so Jupiter isn't really a planet by the definition.
That's interesting. Yeah, and if you look at the solar system, if you look at the dynamics of the solar system, that is primarily driven by the mass of Jupiter and Saturn. So if you look at kind of the orbit of the sun, around this kind of non-central point, as you say, that can pretty much be mathematically explained by just Jupiter and Saturn, I believe, because all of the other planets are small or super far out and they don't have as much of an impact.
So that's a really good point, because we're kind of touching on one of my things that I can never really get my head around is how do solar systems like our own stabilise out when you've got infinite possibilities of when planets are orbiting each other of suddenly an orbit not working.
Well, I mean, there's a few ways of thinking about it. One is that you don't have a case, well, maybe you do, I don't know, but in terms of planet formation theory or like how these kind of systems evolve, it's not like you have a star that's flying through the galaxy and it picks up some planets as it goes along. That may well be the case. But largely it's thought that planets form in around the early forming star, right? So if you have a star at the beginnings of its formation, it will tend to have like this giant dust cloud around it, and as those dust particles interact, some of them might start to clump together. Then those planetesimals might start clumping together to create a planet, and you kind of get this natural formation of this kind of protoplanetary disk, as it's called, starting to form into a planetary system.
What I think is a really good visual aid for that is when you're rowing. Sometimes when you put your row through when you row through the water, you can see that you've created a big spiral in the middle, and you can see how that would collapse. But you can also see the little eddies that come off.
Oh yeah, that's true.
And I always think, if that was like a solar system, those would then be the little eddies that would form your Jupiters that would then be in orbit round thing. And I always think that's a really good...
That's a nice image.
That's nice.
Are you Oxford or Cambridge? Just curious.
Salford? Did they?
No, I don't think so. Anyway,
that's one of the things that people find fascinating as well. The fact that the planets orbit in a disk, and that's obviously one of the reasons why they do is because of this spinning.
So that kind of supports the theory that you have this spinning gas disk that then becomes... Oh, it's getting dodgy outside.
Sorry about that. We are in West London.
So that's kind of one of the reasons why you have this kind of... Well, it supports the theory, right? That you have this... Originally, you have a dust disk, and then the planets then naturally form in the disk. In terms of planet formation, you kind of end up getting these planets kind of dotted in and out. But as we've mentioned previously, exoplanets are not necessarily like our own solar system. So we see a lot of what are known as hot Jupiters. So these are large gas giant planets like our Jupiter, but are orbiting very, very close to their host star. And that's something that we can't properly explain yet in terms of our understanding of how planets form. Because if you think about that dust disk that kind of hypothetically is the creation material of the planets.
Yeah.
The closer you get in, the less dust you have, because the radius of that kind of ring is smaller. So it's difficult to understand why you get these giant planets forming so close to their star.
So you get a lot of migration, don't you?
Yes.
Early on in when a system's forming, and there's that really brilliant. I think it's French animation. Some French scientists have done an animation of how. I think it's how Neptune ended up where it was.
So I think you're thinking of the Nice model.
Ah, there we go. There we go.
Which is it's a
Nice,
fantastic.
Nice is in France.
It is, yeah. You got the country. Yeah.
I'm good at geography as well. Yeah.
I'd recommend looking that up on YouTube. So this is a theoretical model that looks at the dynamics of the solar system, and it explains to an extent how the solar system became the way it is. It's really cool because you can see the planets in these kind of like stable orbits.
And then suddenly it goes all wrong.
Then it goes crazy.
It goes crazy, doesn't it?
Yeah. So you have this kind of inherent instability in the system. You run the model, you end up with this period of heavy bombardment, which is when you get comets and asteroids kind of flying all over the place. Two of the planets, I can't remember which ones they are, but they flip places, so they kind of completely swap. You get this huge kind of instability, and then the planets kind of settle down into their end state, so to speak, i.e. the state that we see them today.
Yeah.
Are you absolutely certain that they do end up in an end state? Because this is what, if you look at the Nice model animation, they seem to be happily going for millions, if not billions. I don't know what the time period is, but they seem to be going for a long time before the resonance between Saturn and Jupiter just send the whole thing crazy. And it's just like frightening when you see it. It's one of those things you think, well, can that not happen again? That's what I'm talking about, the stability of a system.
Yeah, so if you look at the Nice model, again, so it's a theoretical model, so you can get statistics kind of thrown in and figure out what's the most likely case of what you'd see. There are, if you run that model forward in time, so not just looking at how the solar system originated, but what might happen in the future, there's like a 1% chance that Mercury is going to fly into the sun. You've got all these kind of potential scenarios that can come up, and I guess that kind of represents a potentially chaotic system, right, where you've got this inherent instability.
Yeah. Well, I mean, one of the instabilities could be this Planet 9 that keeps swooping around.
Yes.
Yeah,
yes.
So, which may not have formed in the solar system and has been sucked off another one of the sun when it was born in a nebula. Apparently, had its brothers and sisters born in the same nebula. They think it may have. I mean, it's obviously super theoretical, but it literally, you nicked a planet off one of its neighbours.
That's really cool. Yeah, I mean, so that's again. So
otherwise, you couldn't explain how it was so far out.
Yeah, no, it is super far out, right? So Planet 9 is a theoretical discovery. We'll go with discovery, right?
Discovery,
So I guess that's a really interesting point to raise at this point of the discussion, right? Because the way that planet was discovered was by looking at the orbital dynamics of the current planets in the solar system and saying these are a little bit off. How do we make the dynamics of the system work? And the way that scientists at a number of different institutions, I think, have kind of been looking at this, have made the equations balance is by throwing this Planet 9 into the system and saying, right, okay, so that balances out the dynamics, then we've just got finer things.
Yeah.
So.
Ironically, the lead scientist was the guy that demoted Pluto in the first place.
Yes, so Mike Brown at Caltech, right? Yeah.
What a naughty Norman.
Yeah.
Well, I mean, it's karma, isn't it? You get rid of one planet and you introduce another.
Well, there's a lot of talk that they're actually going to say that they're going to, again, completely change the definition and say it's just bodies that are big enough to round themselves off. So we're suddenly going to have 250 or something planets.
And then we'd have loads of them, wouldn't we? So the current definition that I understand is that the body has to be kind of roughly spherical, like you say, but it also has to have a kind of carved out its own path, right? And I think that's one of the reasons why Pluto was demoted, is because there's a number of different bodies that are kind of orbiting in the same
and it's surrounded by
and there's things that are further out that are much bigger.
But then saying that, Jupiter hasn't cleared its path. It's got its Jovian, what they call the Trojans all around it. So.
Exactly, yeah, so there's plenty of satellites there.
And it doesn't even orbit the Sun, as previously.
There you go, you heard it here first, right? Jupiter's gone.
We've got to get rid of Jupiter.
So for people like me who have never really thought about it, why are planets round? Why are they a sphere?
Well, I mean, you could think about it in the same way as why do you get smooth rocks on the seashore, right? If you have this constant bombardment by different asteroids or just generally kind of being hit from other things, it knocks off the chips. So if you had, I don't know, let's say hypothetically, you had a perfect square cube planet.
Yeah.
Okay. Every time it gets hit, it's going to get knocked off the corners, knocked off the edges. Those parts are going to get chipped off. Similarly, if you think about the gravitational pull of a planet, it's hard to kind of explain, I guess, on Earth. But if you're in a vacuum and you get, a drop of water, right, it's going to form a perfect sphere.
Well, yeah, you see the astronauts when they on the International Space Station, that all the water just goes into a nice little ball of spheres.
Mm-hmm. Yeah, so you've got
that's electrostatic charges, isn't it, rather than gravitational charges? But it's the same thing, isn't it? That you've got.
And I guess something's got to do with just the nature of an orbit as well, hasn't it?
Yeah, that's an interesting one. I'm trying to think if that would affect the orbit of the planet. It might affect the spin of the planet. So if you had like a dog bone shaped planet.
If it's going round, that anything chipping it is going to be different than if it did a figure of 8. It would look slightly differently, wouldn't it?
Going back to this kind of double orbit thing, we can bring it back to the world of exoplanets because there has been a planet that has been discovered that is orbiting 2 stars. So that is it is called Kepler 16b, and it's a planet which is going around 2 stars, so a circumbinary planet. And that is an example of one planet orbiting two different stars, which is kind of cool. So I don't know if it looks like a figure of 8, but that's kind of one way to think about it.
That's as close as you'd get.
Yeah.
So what other interesting stars are there? We've just talked about one that orbits 2 stars. What about rocky planets?
There are plenty of rocky planets that have been discovered, which is very exciting. One of them is Kepler. I'm just going to keep giving you Kepler planets, but there's so many of them. One of them is a Kepler 186f.
Okay.
So that was the first rocky planet to be found within its habitable zone. Right. So that is a planet that has a terrestrial-like surface and is at the theoretical temperature that could support liquid water. So there are a number of these kind of planets that have now been discovered thanks to Kepler, which is
Kepler 186f. So is that the 186th star that Kepler's looked at, and therefore the B, C, D, E, F, 5th planet out?
I'm not sure on the 186. It definitely was discovered by Kepler. It's definitely the 5th planet out, hence the F. I don't know what the numbering system
interesting, because TRAPPIST-1, it can't be the first star that it looked at.
Probably not, yeah.
Or maybe it's just the most significant.
The most exciting.
Maybe we can get listeners to write in what their thoughts on that one.
Yeah, we'll have
We'd like to hear from you.
Yeah, good.
So what would you say, Harriet, what's your favourite exoplanet? What would you think's the coolest one for you?
I think my favourite has to be Proxima B.
Yeah.
Because it's so close.
Yeah.
It's within reaching distance, right? I mean, 4 light years is a very long way. Let's not get too carried away.
Yeah.
But that's potentially visitable in our lifetime. That's pretty cool.
And also, I'm not the type of person that likes to take one data point as like the be all and end all. But it just seems incredible that our very nearest star has potentially a sort of Goldilocks planet going around it. It just seems too bizarre. Too good to be true, doesn't it?
Let's hope it isn't.
Yeah. Or, I mean, maybe it's another example of the fact that planets going around stars are not uncommon.
Yeah. Right?
They are everywhere. On average, every star you see in the sky has at least one planet going around it.
Well, I think that's the exciting thing about TRAPPIST-1 is that it does kind of edge ever more to, oh my god, there's lots and lots of these planets. And one of the, particularly around cool dwarfs, or super cool dwarfs, is because they're so much more common than main sequence stars like the Sun.
Yeah, they are the most common type of star in the galaxy, which is convenient because they're also the easiest for us to spot the exoplanets around, as we've mentioned before. So yeah, there's lots of advantages.
Now, Matt, you had an interesting Bill Nye quote.
Oh, did I?
That you brought out.
Oh, yeah.
Would you like to say it again?
Well, I saw it on a meme, so it might not be Bill. It might not be Bill Nye that said it, but the quote
down with the kids
was that if you were Galileo and you had and humans had developed on one of the Trappist planets, like let's say D, for just
Why not?
for D. Yeah. So they've developed on D, and they can see E, and E every now and then appears in their sky twice as big as the moon. And that's roughly how much these things are bigger. And looking through his telescope, he might be able to see traces of a civilization before he's ever set sail to go to the Australia equivalent of that particular planet. Yeah, so it'd be easier for them to see civilizations on their other planets than it would be to visit the civilizations on their own.
Let's just pause there for a moment.
Dramatic pause.
Yeah, it is pretty incredible, that one.
You can get carried away with I can't help it.
Yeah.
And long may it continue.
And if that planet is the 0.9 times the size of the Earth one, it's easier for them to get off and go visit their mates.
And as we said in last week's podcast, you can't help but thinking if there's life on other planets that they look human, which is so wrong.
Well,
of course, Stephen
Jay
Jay Gould saying evolution is if it's like a tree with branches that come out. Mm-hmm. If you rewind and do the same again with exactly the same temperatures and everything else, same bacteria, it won't do the same branch, of course. So imagine that. 4 light years away.
But there's also convergent evolution where you've got dinosaur fish that look ever so much like dolphins, and they've got no common ancestry whatsoever. So you could expect some things.
So what you're saying is it's going to be dinosaur fish.
I really like the concept of having a starship. Let's call it the Enterprise, and off it goes, and it finds a civilized world, and the only way that the starship captain can get out of some danger is by actually getting off with a beautiful alien. So I think that they must look like humans because it's the only way that they get out of trouble.
I hope you're keeping up, listeners, because there will be a test on mental theories.
So I think that's how it works.
Okay.
It certainly did in Star Trek, and that's presumably the most accurate.
That's a documentary, right?
It is a I
From
think
the
it
future.
Is. If we were conspiracy theorists, we might think it was.
Yeah.
That it's been sent to us.
Let's not talk about them.
Oh yeah. No.
Have you watched?
You'll set me off.
Oh, there's an incredible movie. I can't remember. The name of it off the top of my
it's
head.
got what's his face who died
Alan
recently.
Rickman.
Alan Rickman.
And
yeah.
it's
Ace.
Where some aliens.
Spaceballs?
No,
it's not
it's not
Spaceballs,
that
is
one.
it? It's what is it? It's brilliant.
I can't remember the name, so we're not going to be able to do a shout out. But in that, some aliens have been watching a TV show about space travellers, and they think it's a documentary, and then they come to Earth to try and be rescued by this space team.
The captain, because he's so good. Yeah.
And they're just a bunch of actors, and they've got no idea what they're doing.
That sounds amazing.
Funny.
It is. No, it's a really good film.
Well,
it's a really good
we
film.
will have to tell people before the end of the podcast
what it's called.
that is.
Think of it. It's got Alan Rickman and it's got Sigourney Weaver in as well.
Yeah.
I'm going to look on my phone.
You're going to have to Google this one because it's worth it.
Yeah, it is actually genius film, that is.
That's that's very funny.
Oh, and what's his name? Buzz Lightyear is the captain, isn't he?
Yes, I think
the bloke
he
that
is.
plays Buzz Lightyear.
Yeah, not actual Buzz
Lightyear. I can never remember.
Any
his
idea
name.
when this film was made?
90s.
Yeah, it's very 90s.
Totally your era.
Galaxy Quest?
Yes,
Galaxy Quest.
There we go, 1999.
Yes, they even develop a sort of weird technology, don't they? That's
Oh, it's amazing, yeah. So that the aliens... Oh, I don't want to do too many spoilers because I think this should be homework for the listeners, right?
yeah.
To go and watch this movie. It's fantastic.
But I can see what's really weird when you suddenly thought of that. I'd already been thinking of it because when I just said about it being a documentary set from the future, I said just like Galaxy Quest. I couldn't think of its name. I thought I'm going too off topic, but apparently not. No, it's good.
No, definitely not. So, Harriet, one of the things we want to speak about is the Planetary Society's upcoming projects. We know that there's something called SpaceUp. Should we start with that?
Yes, absolutely. So we are organising a SpaceUp event in London on Saturday, the 10th of June.
Okay.
So please do stay tuned for more information. If you sign up to our newsletter, which you should, we will have all the information about that coming up. It's going to be a kind of day-long event. We're going to have some really exciting speakers coming along to do some talks. But the kind of main focus of the day is just to bring people together to talk about anything and everything they want to, related to space, astronomy, all those kind of things. So it's meant to be a very interactive day where people can come together and talk about
Sounds
space
great.
stuff.
Anything else coming up? Any other projects?
Oh, that's the big one for now. So we're currently kind of finalising list of speakers, sorting out the venue. We'll be announcing ticket details kind of nearer the time, so do stay tuned.
Remind us of how people... what's your website address?
So we have a Facebook page. You can find us online, which is Planetary Society London. We also have a monthly newsletter that you can sign up to.
Which is awesome.
Hopefully that they can... yeah, thanks for the shout out. You kind of do this reciprocal arrangement, right?
Yeah.
But yes, so hopefully the details of that will be on this podcast.
Certainly will be.
Info page, so we can
Totally.
put that up there. That's just a monthly newsletter that we send out every month, as you'd expect from a monthly newsletter, which has a list of any and every space event that's going on in London, so not just ours, kind of everything that's going on, some cool space news, and kind of updates on how you can get more involved with the Planetary Society.
And if someone wants to find out more about not just the Planetary Society, but about exoplanets in general, are there any websites or YouTube videos that you can think about that maybe might inflame someone?
Oh, I don't know if you just
Here we
saw my
go.
face.
Harriet
but
got her
I-
hands in the air.
Okay, so, I mean, there's a few serious ones. So one, NASA has loads of information. One
Sure.
about TRAPPIST-1, they've got a really cool website on
In
there.
fact, the TRAPPIST-1 one is unbelievable, isn't it? It's absolutely amazing.
TRAPPIST-1. That's not another.
The TRAPPIST-1 one. The TRAPPIST-1 one. It's a
heard
bit
about
like
this.
it's a bit like the one you phone if you're feeling a bit ill.
Oh yeah.
That's a TRAPPIST-111. But no, it's amazing, isn't it? But
Really interactive,
which-
loads of information. Yeah.
lots of really cool illustrations of planets, and you think, oh, that's what they look like.
Yeah.
But I'm not sure they do.
Okay, so we got the NASA. What else is
Yep, NASA also has
But what was the face lighty up moment?
So you have to go on YouTube and Google. That doesn't make any sense.
Well,
You
it
have to go
does.
on
Well, Google-
YouTube and YouTube.
YouTube. But it is Google. It is Google
It
inside.
is.
Yeah, it is
Yeah,
Google.
that's very true. That's
Yeah.
very true. There is a fantastic a cappella video on the history of exoplanets. So
Whoa,
if you type
wow.
in a cappella history of exoplanets Aladdin, someone has created a 8-minute montage
What?
of a cappella music to Aladdin songs, I think. But the lyrics are all about the history of exoplanets.
Whoa.
And it's amazing. It starts in 1995 when the first exoplanet was discovered. It goes through all of the history of the latest discoveries.
What was
and
the first exoplanet, by the way?
It was a giant planet orbiting around 51 Pegasi. So that was the star.
You thought you were going to catch Harriet out.
No,
there.
I don't
Yeah,
And
no,
you
I have
didn't.
my facts
She's
prepared.
prepared.
Yeah, so this was an exoplanet which was orbiting a main sequence star. I believe it was discovered using the radial velocity method. So that's the method of looking at the different shifts of the star wobbling as the planet orbits around it. That was discovered, like 22 years ago now. And
Right.
Have we actually pictured an exoplanet? Is there a direct observation?
There is, yeah. So some of the methods we've already talked about. So we've gone through transit, we've done radial velocity. Another method that can be used to detect exoplanets is direct imaging. So the technology is now sufficiently good that we can look at stars and directly image planets that are going around them. So that is looking at the light that is reflected off the star, reflecting off the planet, and then coming back down to us.
How do we control the light coming off the star so that it doesn't bleach out the image on that?
So one of the things that you have to do with direct imaging to greatly improve the contrast is block out the light from the star. So in the same way that if you put your hand up to the sun, you shield your eyes, you can see much clearer, right? You're not blinded by the sun. You can use a coronagraph to block out the light from a star, and then the light from planets is much easier to spot.
Yeah, and one of the things that I've seen quite recently is, I think it's NASA, I think, are doing it, is a space-based chronograph of actually flying out this thing that sits in front of space-based telescopes.
Yes. So there's so many telescopes and projects that going on will be coming up in the near future, which are incredibly exciting, to try and detect even more exoplanets.
Absolutely.
One of those is going to be called WFIRST. So this is going to be a direct imaging telescope that's going up. I think it's the 2030s, so it's kind of a little bit far-fetched. Maybe it's late 2020s.
I'll be gone by then.
Do you mean 8:30? Or do you mean the year 2030?
I mean the year 2030.
Matt's getting really excited that we're close.
It's
literally
going on now.
It's actually
now. It's 8:30 now.
No, but that is going to be using this direct imaging technique, and I think that they're planning to send up one of these, like you say, this sail that's going to block out the sun to use it.
So with something like James Webb Telescope, what's your thoughts on that? Obviously incredibly exciting. We've put some pictures up on the blog and it looks incredible, and I can't wait till it goes up.
I'm just too stressed about it. I'm still stressed.
Yeah, Matt's very nervous about it, but what are your thoughts on that?
I was watching a documentary about it the other day, and it makes me so stressed just thinking about the number of different things. I think it said there's like 137, I think, different processes that have to happen perfectly for it to come out and set itself up in space.
But that's a bit, to be fair, that's a bit like the Philae lander and everything that had to happen with that.
Yeah,
and all those little burns, and you think they are really good with the big projects. They work really well.
We just hope that it's not going to do what others have done. And
it's the Hubble one. The Hubble one is just the memory of Hubble being wrong is too horrific.
And the thing is, so Hubble was is pretty close to the Earth, right? So astronauts were able to go up and service it, right?
At great difficulty. Let's not
trivialise this, right? But with James Webb, it is going to be, I think it's like 1 million kilometres away from the Earth. We're not going to be getting...
you can't just nip over with a screwdriver.
You can't just go and say hello and fix it. No,
it's a Lagrange point, isn't it?
Yes.
But L2, is that
L2, yes.
And,
so
why do they put it at... Why are they going to put it so far out if it's a disaster if you can't fix it?
So we've talked about orbital dynamics already. One of the interesting things that if you look at kind of a two-body system, so looking at the Earth and the Sun, looking at the dynamics of that system, you get what are known as Lagrangian points. So there are 5 Lagrangian points in this two-body system, and these are points of stability, right? So if you have the potential of the star, the sun, and the Earth kind of cancel each other out at these points. L2 is one of these stable points. So it's a really great spot to put telescopes because you don't have to tweak it too much and it will kind of stay where it is. Yeah.
Interesting.
Hubble just orbiting around the Earth, right? But the James Webb is going to be super far out in a fixed point and will be staying there.
So let's hope that it can fix itself if anything does go wrong.
Yeah, well, I mean, I wonder if they would ever, maybe with all SpaceX and SLS and all these other ones, New Glenn, that maybe they could fix it if it was in a real, because that's a lot of hardware just to leave out there rotting, particularly the mirrors.
Those beautiful gold mirrors.
Beautiful gold mirrors. We can't just leave it out there.
Do you think it's like how frustrating it is when you get back from the shops and you realise you've forgotten the milk or the bread, and someone goes, "I'll go." Do you think it could be similar to that?
I think it'll be a similar sort of.
Oh, what did we forget on the James Webb? Get back.
No, the worst is if it's one of those hideous things like, we got some Russian parts, but they thought we were working in meters, but we were working in feet. So no,
that's very Spinal Tap, isn't it?
Well, it's very space.
That's happened before, hasn't it?
Yeah, a couple of things are smashed into Mars because of that.
Yeah.
It's like, you were working in
Yeah.
Oh God, I'm going to be very, very tense in 2018 when
I've got a good
up.
feeling about it. I think.
It's going to be amazing. So, what is there any other? So we got WFIRST, and was it called WFIRST?
It was called WFIRST. Yeah, I can't remember what it stands for.
James
exciting.
Webb, the JWST.
We've got TESS. So, I mean, I don't know how astronomers come up with these cool nicknames, but yeah, so we've got the Transiting Exoplanets Survey Satellite, TESS. So that's going to be going up again in 2018, same time as James Webb.
Is that a sort of Kepler replacement, or is it a bit even more powerful than Kepler?
So it is going to be, I guess, kind of a follow-up to Kepler. So it's using the same technique, still looking at transit, so looking for those dips in the stars. It's, from what I understand, it's slightly less precise or accurate. So the precision of the measurements is kind of a little bit reduced compared to Kepler, but it has a much greater field of view. So instead of looking at one very small section of the sky, TESS is going to be looking at hundreds and thousands of stars.
Right, so it's a bit more. There was a recent European mission that pretty much mapped every star.
That's right.
Gaia,
yeah.
So
named after another role.
Named after another Roland synthesizer. Yeah. Available from all good music stores.
There you go. So we've got TESS going up. That's quite exciting.
Yep.
Another one is we've got the Planetary Transits and Oscillations of Stars, affectionately known as Plato.
Plato.
So that is a European Space Agency project, actually. So that's a space observatory that's under development. That's going to be going up in 2024.
That's a bearable time frame.
Good work, ESA.
But 2030s, I'm just...
Bit too far off.
Just too far off, and that's why I was a bit depressed about the Europa Clipper.
Yeah.
Gosh, when's that going?
It's like something like 20 in the sort of 2024, but it won't get to Jupiter till the 2030s.
Oh yeah. It's a long way, isn't it? You'll still be doing podcasts by then.
We'll
podcast number 1000.
Exactly. We might be hitting the 1000th episode. That's a very good point.
Yeah, you should try and time it, right? Do like the big podcast 1000 should be a very...
It's got 100 every 2 years, so it'll be 20 years. 20 years we'll get to 1,000.
We'll have loads more grey hair than we already have.
But so many more exciting discoveries.
This is it. Each one is a story.
Yes, totally true. I mean, imagine how many times Harriet will have been on by then.
Yeah, that's true. Yeah.
Plenty more podcasts to come, right?
Even Harriet will be old.
I don't believe it.
Time passes for everyone, right? So,
it does, alas.
Yes. Oh, alas.
So, is there anything else that we need to cover?
One thing I would like to say at the end, if that's all right. In terms of listeners and how they can get involved, right? So we've talked about NASA website, checking out that YouTube video of the Exoplanet a cappella story, which is very, very funny, I have to say. But there's also ways that people can do this kind of science themselves, right? So if you haven't been on Zooniverse or looked at citizen science already, please do. It's a fantastic website that allows people to get involved and do real scientific research or contribute to real scientific research. One of the projects that you can get involved in is called Planet Hunters. So that allows people to actually look at this radial velocity data and look at, I think it's radial velocity, I'm not sure. Anyway, look at this data.
Well, actually, the one that I did was actually, light dip data. So,
so it was transits.
Yeah, so it was transits.
Okay, there you go.
And you kind of, because your eye is better at seeing the pattern than even the best pattern recognition AIs are still.
We can still beat the machines at something, right?
Absolutely.
I don't know how for long.
Yeah, probably not much longer.
No.
But so that's the one way people can get involved. They can actually look for planets themselves, which is really cool. Another way is by supporting the Planetary Society.
Hey,
so one of the things that the Planetary Society does is fund exoplanet research. So that is a great way. If you're interested in becoming a member, you can sign up online.
We just got our membership cards.
Yeah.
Please get involved yourself. It's amazing.
I might even take a picture of Jamie in his t-shirt.
I think you should.
Yeah. It's a strong look.
People want to see it. That's the news.
Yeah. Oh, right.
Exactly. So there's loads of different ways to get involved, and the science ain't stopping anytime soon. I think we can.
So we could be proud of ourselves, Jamie, that we've helped. That maybe we'll help in the future. Just tip the balance to find life on another planet.
Well, if I know our listeners, there are literally tens of them that agree. And oh dear.
Well, you know I always cut that out, Jamie.
I know. I try and get that joke in every podcast.
And then I always cut it out.
I demand it be left in. Well, Harriet, thank you so much for joining us again. This is for the second time. Please, as Harriet said, go to the website. please check it out. See if you're free on June the 10th to go to SpaceUp. Sounds amazing. And we'll see you in podcast 27.
Awesome. Thanks, Harriet.
Thank you. Bye.